All right, good morning, everyone. Happy to be back. Quick show of hands, just for my benefit. Who among you were here yesterday and saw the first presentation? Oh, wow, okay, good, fair number of you. Good, then I won't spend too much time going over the same information. I will just recall some of the key elements before diving in. I really want to take the time to expose to you the different problem statements that underpin the challenge, and then give you the opportunity to ask questions. Good, so as I mentioned yesterday, Airbus has a long tradition of deploying a high-performance computing solution for some of the more difficult challenges that we face in the aerospace industry. But we realize that classical techniques, classical methods, are slowly approaching their limits. A lot of them governed simply by the physics at the heart of these computing systems. And we also realize that quantum computing can offer and deliver a new series of potentials by harnessing a very different physics at the heart of their systems. And we're not satisfied to just be on the sidelines and see this transformation happen. We actually want to be a part of this paradigm shift. And that's why we've decided to launch this challenge. That's why we're looking to help solve these key aerospace problems, but using quantum computing. Now, flight physics, as I first exposed yesterday, is a really broad topic. It impacts virtually all aspects of an aircraft's life, from design all the way out to operation. And really, for airlines, it's also part of their bottom line. So for us, it felt natural to try and pair what is a very important, deep-rooted change in the computational world with something that is sort of transverse and fundamental to many aspects in the aerospace sector. And that's why the topic was selected. So in launching this challenge, we're looking to draw ties, draw connections to the quantum community, add ourselves to that debate, and that brings to the third point, the benefit for winners. What's in it for the participants, those joining this effort? Well, all of us gathered here at the Quantum to Business conference, I think, have one very important goal in mind, one common goal in mind, and that is to show that quantum computers can provide a demonstrated advantage for real industrial problem. And that's exactly what we're trying to achieve in launching and carrying this challenge. We want to add ourselves to the community, and we're going to bring forward what we know best, what we're best at, which is this deep-rooted knowledge in aerospace sector. So for the winners at the end, we hope to provide access to hardware, the tools needed, and ourselves, a collaborative environment working with our flight physics experts to bring these best ideas to fruition. Now, the challenge will be run through most of 2019. It'll be launched early next year. There'll be a first sort of submission deadline at the end of 2019, and those submissions will then be reviewed by a panel, a panel of experts, both from the aerospace sector and the quantum computing sector. Participants can come in as individuals, as teams, however they like. And we'll be interacting with them through most of the year, trying to answer questions, give clarity as much as possible on the different problem statements. We'll be announcing the winners at the very end of 2019, early 2020, and with those first series of winners, again, going into sort of a second phase, working directly with them, getting the hardware, and trying to bring these ideas further. Okay, I said I would keep the introduction quick and simple. Let me dive to the important thing. What are the problem statements? There are 5 of them that underpin the challenge, and I'll go through them one by one. So the first one is the aircraft climb. As you know, you've all been on an airplane. There are different phases to an aircraft's flight. The cruise is typically the longest one, and researching the optimal cost-benefit of a cruise has been at the heart of a lot of science, treating airline characteristics and airline advantages. However, with more and more short-haul flights, short segments between 2 rather close cities, the climb and the descent are actually gaining in greater importance. And for the airlines, better understanding both of those segments are quite important. So, as part of the challenge, there we are. Well, there we are. Sorry about that. So as part of the challenge, we're bringing forward this climb. We're looking at the climb segment, and we're hoping to be able to identify where gains can be had. At the heart of it is a fine balance between time, which is especially the cost of the human resources on board, the pilot, the staff, and the fuel burn, and trying to optimize that. The second one has to do with computational fluid dynamics. The efficiency of an aircraft's design is intimately tied to the quality of the aircraft design, which itself is based on computational fluid dynamics. CFD simulations demonstrate how the air flows around the aircraft structure and also characterizes the aerodynamic forces that act on the surfaces. And we, of course, have to respect certain criteria, certain limits imposed by different flight authorities. Now, traditionally, CFDs are very time-consuming. They are complex, and they require both long lead times, design times, and deep computational resources. So this challenge is intended to show how CFD simulations can be improved and can be treated either in a fully quantum mechanical way or, probably more likely, in some hybrid quantum classical fashion. And we also want to see how the solutions to that particular challenge would scale with complexity of the problem and scale with computational needs. That's the second challenge. Good. The third is partial differential equations. PDEs is also, by the way, part of the second challenge on computational fluid dynamics. But PDEs also are present in a number of different aerospace problems. Their resolution requires complex modeling, complex investigations, and traditionally it was done in a deterministic fashion with numerical methods. Okay, great. More recently, we've been looking at neural networks, deep learning methods to try and improve on that, where the PDEs are now solved in a completely different way, and the equations themselves are used for the backpropagation in a PDE, for those of you who are familiar with that. Of course, neural networks has also, I think, been an interesting new component to the quantum computing community. And so we want to challenge the community to try and do just that, to augment neural networks that have been designed for aerospace partial differential equation problems with some quantum capability. The fourth problem statement is most certainly the most complex problem statement. It's about multidimensional design, where we're looking to try and bring together different features. So in classical computing, given its limits, the aerospace industry, when we're doing our design, we're limited in the ability to bring together different coupled relations. So for example, when looking at a full aircraft design, we want to be able to bring together the airframe loads, the mass, and the structural analysis all together. But today, again, given those classical methods, we have to decompose that. And so all in all, this can cause long design lead times, convoluted processes, and conservative estimates. So we're looking for a potential paradigm shift by leveraging what quantum computing can do quite well, which is an augmented and increased search space. By having this wider design space, we're hoping to be able to evaluate different parameters simultaneously, and thus be able to both preserve the structural integrity and optimizing the other supporting characteristics, such as the weight of the aircraft. So this balance is especially important for one segment, one part of an airplane, and that's the wing box. The wing box has very, very delicate, very careful balance between all three characteristics. And again, we're turning to the quantum computing community to help us out with that. The fifth problem, the last problem, is one I think that's very standard or can be found in many different areas, many different industries. It's also true in the aerospace industry. It's the aircraft loading optimization problem. The objective here is to be able to optimize how the belly of the aircraft, the payload section, is actually filled. So airlines typically use that as a capability to try and increase their revenue, be able to transport a few more materials, but also want to limit the amount of fuel burn that that extra weight brings on. The scope, by the way, of this optimization is also limited by the operational envelope of the aircraft, such as the maximum payload it can handle, the center of gravity of the aircraft, and the shearing forces that act on the fuselage. So this problem is a typical optimization problem with constraints, and we want to see how quantum computing here can help, and again, be able to scale with the size problem and the computational resources that goes along. Good. I've gone through all 5 problem statements rather quickly. I promised a lot of questions, so I'll give you ample opportunity for that. Before opening the floor to questions, I do want to state that when the challenge will be launched in early 2019, each of those problem statements will come with more than just the few sentences I've given for each of them. They'll be full, what we call technical dossiers, with the mathematics at the heart of these problems to try and give good reference points to the quantum computing community, help them get a good sense of where the aerospace challenge lies behind each of these problems, and give them that starting point from which to work from. For those of you interested, I encourage you to go on the website now. You can put in your details, and as soon as the challenges launch, those technical dossiers will be sent to you. You can choose all of the problems you want to participate in, and we'll be sure, of course, to keep tabs throughout the year. So on this point, I'll stop and give you the opportunity to ask questions. Thank you. We've got one here in the front, one here as well. I think there's a gentleman here as well for the second question.
Hi, great. I fully support this effort. I think it's really important for quantum computing practitioners to have real-world potential problems to tackle. It's going to inspire, I'm sure, a whole set of new quantum algorithms. You say that you're interested in possibly quantum classical approaches. Mm-hmm. What is the boundary where you draw a line like this is not quantum enough, or?
Okay. So the boundary we're drawing is not on the degree of quantumness. It's on the benchmarking, the comparison to, say, a pure classical method approach. So for us, it's more on the comparison, on the benchmarking, than on the degree or the role that the quantum computer plays. So we're very open, very flexible as to the ideas that are brought forward and where each team or each participant draws that line. We actually want to leave kind of that freedom to those participating. Yes?
So I'm just curious about how real these problems are. So for example, the climb optimization.
Yeah.
Right? Are we going to have real aircraft performance models? Are we going to have to worry about things like limitations of the flight management system?
Yeah. Can we go back in the slides? Super. Let me see if I can go back. There we go. You'll see in the technical dossier, we're defining exactly the starting point and end point to meet precisely that. So the starting point is not the runway. It's the first 10,000 feet, so you have to clear the runway, clear the airport area. And then from 10,000 feet to 36,000 feet is where you have that climb, that climb. And the climb is intimately related to the air characteristics around the airport at that particular time of day. And so we're bringing that or feeding that as part of the model to try and investigate what is indeed the right path. Today, those characteristics are typically programmed into the aircraft's computer. There's only so many waypoints that you can do. Yeah. We're looking to try and free that characteristics or free that constraint and see what can the community propose that might go beyond what we typically do today for that segment.
I have a question on the limitation of the number of qubits. So can this go against the simulator, or do we have to actually have a device that has enough bits for this? And if so, do you have an idea how many bits we're going to need?
Okay, so the question, if I've understood you correctly, the question is about, do we need to do something more than the quantum simulators can produce? And if so, how many qubits would we need in order to get there? Did I get you correctly?
Or we can use a simulator.
I think so. The simulator, I think, is a fine approach. Again, for the first year, for the first, say, 2019 phase of the challenge, we're mostly expecting ideas, algorithms, methods, techniques. Perhaps some of the participants will already have access to simulators and other capabilities. Great. we certainly would welcome that as part of the answer. Moving into a second phase, and again, keeping in mind that for us, the ultimate goal is to actually bring this into full use, full production. We'd want to keep sort of advancing the idea as the technologies, the hardware or simulators keep advancing. So we're sort of hoping to carry this forward over a rather extensive period of time. I think there was a question a little bit forward here.
Sorry, it's related. I guess, are you welcoming also algorithms that would require full fault tolerance that cannot be run on even simulators? Yes, we would welcome them. When making the evaluation, when trying to ascertain what is the best idea, which one we want to move forward with, I think we'll, of course, sort of keep that in mind and keep that in relation to the others. There's one at the back.
Yeah. I had the sort of complementary question. What if someone found a much faster way to solve one of these challenges than anything currently known, but without using any quantum ideas at all?
To be honest, and that kind of goes back to the first question, where do you draw that interface? We're happy with that. We're quite happy with that, with those capabilities. But so sorry, we kind of leave it to the community as well to bring forward what they think is the right benchmark, right? So we have our own system, our own capabilities with many of these problems, and we'll leave it to the community as well to propose maybe, hey, purely classical approaches if necessary.
There are hundreds of different problems. How did you arrive at those 5 problem statements, and what was the process?
Yeah, no, that's a good point. So indeed, there are many different problems. Even within flight physics, there are a lot of them. When we came up with these 5s, we brought together flight physics experts and experts from QC Ware to work together and try and identify those that were most likely to find echoes within the quantum computing world, and where quantum computers could potentially bring an advantage. Sorry, I think you have a follow-up on that?
So a lot of those problems are optimization problems. Have you considered doing any advanced materials problems, like composite material design and other types of problems?
We have. We felt that these 5 were the 5 best ones to start with. And I think to that point, it's going to be a learning experience for us as well, right? So this challenge is something new, certainly in this space. It's very new for us. We're going to learn as we go along over the year, over the coming year. If we're very successful, and we certainly believe that this can be deeply impactful, then I think moving forward into 2020 and afterwards, we're happy to bring in new different problem statements, and why not on materials. Any other questions? Okay.
One more question.
Yeah?
Will you be making data available?
Sorry, where?
Over here.
Over here. Oh,
Will you be making data sets available for each of these?
We will be providing some data sets for a few of these problems, and to the winners, when we carry this forward, we'll be exposing all of the data that supports these problem statements. I think there's one at the very back here.
So what's the price?
Sorry?
What's the price?
Can we go back again? Okay, never mind. There we go. Yeah. Good. When we thought about this problem, when we thought about the challenge, and we thought about how it would evolve, for us, it was clear from the get-go that we wanted something long-term. And so to make this happen, what we wanted to do was not come forward with just something short-term. We wanted to come forward with a true commitment on what we could do best, on what we could bring most, and that is ourselves. The knowledge, the people, the data, the time. And that's why for us, the prize, if you wish, is the follow-on. It's the access to the hardware. We'll pay for that. It's working with us, bringing our teams, bringing our data, and really trying to bring all of these ideas to full operation.
Let me add something to that. I know it's not fully baked in, so we're not committing to that yet, but potentially we can have the finalists actually present at next year's Q2B if the if all the time frame works. I know it's a little bit tight, but we'll be happy to give them the stage and have them present here and basically get the recognition and the publicity from that. So with that, I'm trying to kind of keep things on time, and we're almost there. Thank you very much, Thierry.
Thank you.
This was great. Thank you.
Thank you.
Thanks.